All right, continuing with chapter 15. And I believe we're on section 4. RC, the reference counted smart pointer. Let's close that. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node, and that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it. So we really haven't gotten into the thick of things yet, but right here they're talking about, well, they're introducing the topic, which is having multiple references. And the example they give, which is a valid example, is graphs and graph data structures. We can have a node and you can have edges that point to it. And it is very common for a node to have multiple edges associated to it. And in those cases, each of those edges own the node. But in terms of borrowing structure, well, you can't have multiple things own a node. So how do we go about solving this? And that's seemingly RC. To enable multiple ownership, Rust has a type called RC, which is an abbreviation for reference counting. The reference counting type keeps track of the number of references to a value, which determines whether or not a value is still in use. If there are 0 references to a value, the value can be cleaned up without any references becoming invalid. Imagine RC as a TV in a family room. When one person enters to watch TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn the TV off because it's no longer being used. If someone turns off the TV while others are still watching it, there will be an uproar from the remaining TV watchers. I see. So here they're defining what RC is, which is reference counting, which is the ability to have something be owned by multiple things. And here, which I really like, is this TV reference, where they describe what it actually means, like how they go about counting. We use the reference counting type when we want to allocate some data on the heap for multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the owner's data, and the normal ownership rules enforced at compile time would take effect. Oh, I really like the way they pointed it out here. So they're saying in the case we use reference counting type are when, one, there are going to be multiple people using this piece of data, right? But more importantly, you do not know who's going to be the last person to use it. Because, well, if you knew who was the last person using it, then you would just make that person the owner of the data, and everybody else can just reference it. So in these cases, definitely use reference counting type. Note that reference counting is only for use in single-threaded scenarios. When we discuss concurrency in chapter 16, we'll cover how to do reference counting in multi-threaded programs. Okay, this could only be used in single-threaded applications. Understood. Using reference counting to share data. Let's return to our cons list example in listing 15-5. Recall that we defined it using box. This time, we'll create 2 lists that share ownership of a third list. Conceptually, this looks similar to figure 15-3. Okay, so they have list A, and they have list B, which starts at 3 and then points to 5, points to 10, points to 0. And they have list C, which starts at 4, points to 5, points to 10, points to 0. List A is a subset of both B and C. However, C is not a subset of B, and B is not a subset of C. Understood. We'll create a list A that contains 5 and then 10. Then we'll make 2 more lists, B that starts with 3 and C that starts with 4. Both B and C lists will continue on the first A list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. Trying to implement this scenario using definition of list with box won't work. as shown in listing 15-7. So let's try to write this out. Bring up the editor. We have enum list, and this is familiar. We have cons. They did I32 again. We have our box. This is a list. We have nil, and then we re-import it just so we can use it directly without going through list and then writing cons and yada yada yada. So create list. Here's the re-importing it. Cons nil. Now let's see how they did this. Let A equal cons. Starts off with a 5. Box new. Put a new line like they did. Cons 10, comma, box new nil. Let B equal cons 3, box new A. Let C equal cons 4, box new A. Okay, so after writing it out, I understand the example. So we have A, right, which is cons, which is going to be a pointer on the heap. Then we have A here and A here. Creating a new box would probably move that pointer. And I think that's why this is yelling at us here. But let's run it. Let's run it. Cargo run. Yeah, so A was moved here. So A no longer exists because it was dropped. And then we try to use A again here. Move occurs because A has type list, which does not implement the copy trait. I.e., if we could copy it, then we could just make A go to both. However, they wouldn't be pointing to the same reference now, they'll be pointing to the individual copies of A, which is not what we want. Understood? When we compile this code, we get this error. Moved A, moved here, and yeah, that's exactly what we saw. The cons variants own the data they hold. So when we create the B list, A is moved into B, and B owns A. Then, when we try to use A again when creating C, we're not allowed to because A has been moved. We could change the definition of cons to hold references instead, but then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. The borrow checker wouldn't let us compile let A equal cons 10 and a pointer to nil. For example, because the temporary nil value would be dropped before A could take a reference to it. Instead, we'll change our definition of a list to use reference counting in place of box, as shown in listing 15-18. Each cons variant will now hold a value and a reference counter pointing to a list. When we create B, instead of taking ownership of A, we'll clone the reference counting list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in the reference counting list. We'll also clone A when creating C, increasing the number of references from 2 to 3. Every time we call reference counting clone, the reference count to the data within the reference counting list will increase, and the data won't be cleaned up unless there are 0 references to it. Alright, so here they covered 2 things. One, they noted the issue, which is the whole moving and ownership. A, like we already stated this, but A comes into here, gets moved into B, A no longer exists, and we're trying to move A into C, but A doesn't exist at this point. They said that we may be able to attempt to try to fix this with references. However, they immediately squashed that idea, saying that it's not going to work. And now they want us to use the reference counting type, which will just clone the pointer to the data that's on the heap for each of these new people that want to own A. So let's try that real quick. They have it down here. So this goes from box to RC. And create lists, cons. Oh, and I have to import RC. That makes sense. And how did this change? A starts out as RC new. Yeah, let me just write this from the beginning because this is a lot of nested things. RC new. Put our cons in here. 5. RC new cons 10 RC new nil that's a long line. Let B equal cons 3 RC clone, and we pass a pointer reference to A. And we should probably do the same thing with C. Cons 4 RC clone pointer reference to A. And let's just run to see if it compiles. It did. It compiled. Alright. We need to add a use statement to bring reference counting type into scope because it's not in the prelude. In main, we create a list holding 5 and 10 and store it in a new reference counting list in A. Then when we create B and C, we call the reference counting clone function and pass a reference to the reference counting list in A as an argument. We could have called A.clone rather than reference counting clone, but Rust convention is to use reference counting clone in this case. The implementation of reference counting clone doesn't make a deep copy of all the data like most types implementation of clone do. The call to reference counting clone only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using reference counting clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones and can disregard calls to reference counting clone. So here they just explain what they did here, which is, we already went over this, but for B, they made a clone of A and passed A in as a reference, and they did the same thing for C, which then increment the reference count on A. So now I think it should be 3. A owns itself, B owns A, and C owns A. And even though this is a clone, this is not clone in the traditional sense where all the data is going to be copied. Instead, the only thing that was copied is the reference. So they created a new pointer to the data on the heap. The data on the heap hasn't been copied at all. And as such, this is very efficient in terms of performance. Cloning a reference counting type increases the reference count. Let's change our working example and listing 15-18 so we can see the reference counts changing as we create and drop references to the reference counting list in A. In listing 15-19, we'll change main so it has an inner scope around list C. Then we can see how the reference count changes when C goes out of scope. Okay? So they have that here. So A stays the same. We print out this line. I think they just copy it. Paste. What does this say? Counting after creating. And here it looks like we're using reference counting, strong count, and passing an A, which seemingly just gives us back the number of references, or give us back the count of references to A. And we do the same thing for B while looking at A. That here. And then we put C in its own scope, so then C will get dropped at the end of its scope, which should be here, and then it should go back down. I see. Copy. Yeah, I'm copying and pasting because this is the same, almost the same line over and over and over again. Let's make this big to make sure we got everything correct. So we create A. We have that here. We then print the strong count for A. Create B, has a reference to A. After creating B, we have a strong count for A. New scope, create C. Creating C, getting the new count. And then outside of that scope, when C goes out of scope, get the count again. All right, let's run this. So count after creating, let me move that over. So count after creating A is 1. After creating B is 2. After creating C is 3. After C goes out of scope, the count is now 2. So yeah, they just want to show us a visual representation of the count of the reference counter going up and down, which they did a nice job of. Make this big. At each point of the program where the reference count changes, we print the reference count, which we can get by calling the reference count strong count function. This function is named strong count rather than count because the reference counting type also has a weak count. We'll see what weak count is used for in the preventing reference cycles turning a reference counting type into a weak type section. Is that this chapter? Not. Looks like it's 15-6. So yeah, it is this chapter. Cool. The code prints out the following, which we already saw. We can see that the reference counting list in A has an initial reference count of 1. Then each time we call clone, the count goes up by 1. When C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call reference counting clone to increase the reference count. The implementation of the drop trait decreases the reference count automatically when a reference counting type value goes out of scope. Okay, So here they're just going over the example going up and down. But one thing to note is what they're stating is that when we want to go up in a reference count, we have to explicitly call the reference clone, or that for us did it. However, when we went down in reference counting, we didn't actually call anything. The drop trait did it for us automatically when C went out of scope and was dropped. What we can't see in this example is that when B and A go out of scope at the end of main, the count is then 0, and the reference counting list is cleaned up completely at that point. Using reference counting trait allows a single value to have multiple owners, and the count ensures that the value remains valid as long as any of the owners still exist. Via immutable references, reference counting type allows you to share data between multiple parts of your program for reading only. If reference counting type allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in chapter 4. Multiple mutable borrows to the same place can cause data races and inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the ref cell type that you can use in conjunction with the reference counting type to work with this immutability restriction. Okay, so some things they pointed out. We didn't get to see the reference count go all the way to 0 because that happened at the end of main, which makes sense. Everything was just cleaned up there automatically. This reference counting type is useful when you have an immutable data source that you like other people to read from. However, at least as it was stated in this section, you cannot use this type with multiple mutable references. But there seems to be a pattern for that, which is they said it here, immutability, interior mutability pattern, which will be covered in the next section. With that, this is the end of the video. I hope you enjoyed it. Hope you learned something. I know I did. If you liked the video, please click like on the video and subscribe. Outside of that, peace.